We will now see how to go around this difficulty of slowly convergent series. Now let's see, all of us know this equation. I mean, we know that tan inverse half plus tan inverse 1/3 is equal to tan inverse half plus 1/3 divided by 1 minus half into 1/3. This is tan inverse 5 by 6 divided by 5 by 6, and that is tan inverse 1, which is 5 by 4. So this gives us a good way of finding the value of pi by a derived series, which is derived from Gregory's series. We will see how this becomes a faster convergent series, not the very slowly convergent series that we first wrote down. For that, I just need to rub the board for a while. If I write tan inverse half, that is half minus half cube by 3 plus half to the power of 5 by 5 minus and so on. And similarly, tan inverse 1 by 3 is 1 by 3 minus 1 by 3 whole cube by 3 plus 1 by 3 to the power of 5 by 5 and so on. Now adding both the series, on the left we get tan inverse half plus tan inverse 1/3, and that is nothing but pi by 4. That is half plus 1/3 minus 1/3 half cubed plus 1/3 cube minus 1 by 5 half to the power of 5 plus 1 by 3 to the power of 5. We can write more and more terms, and we find that the value of pi that we get after taking, say, 4 or 5 bracketed terms is correct up to the 4th decimal place, maybe up to the 5th decimal place. For that, for a comparison, we take the value of pi as given by a calculator. Calculator gives it to you up to about 8-9 places of decimals. So we can compare how much is the accuracy by stopping at the 4th decimal place or the 6th decimal place or the 8th decimal place, wherever we choose. More and more terms reveal that the errors go as low as 1.5 ppm, not percent, 1.5 to 2 parts per million, and that is of course in normal work quite acceptable. Okay, we will now shift to another formula which also gives us the value of pi, but that does not depend on Gregory's series, it depends on another series. Many of us have encountered this formula. The series on the right is nothing but 1 by 1 square plus 1 by 2 square plus 1 by 3 square and so on. In fact, it is the harmonic series of the squares of natural numbers. The squares of natural numbers add up to 1 square plus 2 square plus 3 square. That has a nice formula, n by 6, n plus 1 into 2n plus 1. But here we have written down the series for the sum of the reciprocals of the squares of natural numbers going up to infinity. If the right hand side is evaluated to any number of terms, then that is pi square by 6. Hence, pi square is 6 times the series on the right. Evaluate this to as many terms as you wish, multiply by 6 and then take a square root to get the value of pi. Now, I cannot, whenever I am talking about pi, I cannot help but writing a very, very famous equation, and that invites two other guests. The equation has not only pi as an element, but two other members as elements, and that is the famous equation that is e to the power of I pi plus 1 is 0. In other words, e to the power of I pi is minus 1, where I is the imaginary unit. Okay. Now, this equation is very, very special because we have a transcendental number e, the exponential constant. We have pi, about which we were discussing just now. We have this I. These three people are not very clearly defined as one is. All of us know one much better than we know, for example, E and pi and I. But these three people together give a very, very famous relationship. It's very, very fundamental. It's very, very useful in mathematics. And Srinivasa Ramanujan was actually more or less, he was awed. He was thunderstruck almost to think about this beautiful relation that e to the power of I pi plus 1 is 0. Neither pi nor e are rational numbers. Both of them are transcendental numbers, but they combine to give you minus 1 in this particular way. Now, in our next lecture, we will discuss about approximations and small errors in computation. Thank you.